Thank you. So hello everyone, and thank you for joining me in this talk where we're going to explore the legacy of Joe Armstrong, the principal inventor of Erlang, who unfortunately recently passed away, and so Joe sadly will not be with us anymore. But his work lives on, and this is what we're going to explore today. Basically, whatever I'm about to show you exists first and foremost owing to Joe's immense contribution to our field. And speaking personally for myself, I'm extremely grateful for that. So I've been using Erlang and Elixir for quite some time now. And for me personally, this is by far my favorite part of my own professional career. And with this talk, I basically want to try to spread a little bit of this happiness and explain why exactly am I so excited about these languages. And so I'm going to take you with me into the quest for the soul of Erlang and Elixir. And you're getting 2 languages at the price of 1. And I'm going to throw in a couple of more into the mix. The main reason why I can do this is because I'm focusing on the common theme between these languages, and this is their runtime layer, the Erlang virtual machine, which is also known under the name Beam. And so despite all the differences that exist between these languages, I'm going to treat them as if they are exactly the same, as if they are a mere interface that we use to talk to Beam and harness its power. And so I'm going to be very sloppy about these names. Most of the time I'm going to say Elixir because all of the demos and samples, code samples that you see are written in Elixir. Maybe occasionally I'll say Erlang, but what I really mean to say is any Beam language, because Beam is a focus of this talk from a user's perspective, from a standpoint of a developer writing a Beam-powered system. So the talk is going to consist of 3 parts. I'm going to kick off with a basic introduction to the principles and mechanics of Beam concurrency. And this is then followed with the central piece, which is a demo-driven exploration of Beam concurrency in practice. So we're going to take a look at how to split system into different concurrent parts, and we're going to discuss a little bit why do we take these approaches and what kind of benefits do we get. And then finally, I'm going to wrap up with a short and somewhat controversial think piece exploring a different style of building software systems, a style which goes against the grain of what we're typically doing today, a style which is first and foremost made possible when we have a runtime such as Beam as our foundation, a style which is, in my personal opinion, simpler, yet at the same time more powerful and flexible compared to how we're typically building software systems today. So I have I have a very ambitious plan. Obviously, the time is limited, so I got to warn you up front that I'm going to speak really fast, and I apologize for this, but I do want to share a lot of information with you, and I hope that it's going to be interesting for you and that you're going to get a lot of food for thought. So without further ado, let's kick off with concurrency the way Joe Armstrong envisioned it, this Beam-style concurrency. And the central idea, the central concept here is the concept of a thing called process. And process in Beam terminology is a runtime execution context of code. Any code, like Elixir code, runs in some process at runtime. Now, process is not an OS process, and it is not an OS thread, and I'm going to clarify this distinction a bit later on. But essentially, what process is basically a sequential program. Right, so there is no internal concurrency in the process, and you have regular things happening in there. You're invoking some functions, passing some parameters, taking return values, have some branching logic, have some loops, so on and so forth. Basic programming 101. And as long as it's sequential, we say that Elixir is functional by some definition of functional, not a pure functional language, but it has some functional properties. And then you have this whole other paradigm within the same language, this concurrent Elixir. And to become concurrent, you really need to run multiple processes. And there are a bunch of different ways how you can do this, but the most fundamental one would be this function here from the standard library called spawn, which you invoke to start or spawn another process. So here we have one process, one sequential program. We invoke spawn, we pass it a lambda, an anonymous function, and what happens is a new process is started or spawned, and as soon as that process is started, this process here moves forward. And now in theory, on paper, we have 2 processes running in parallel, or the way I prefer to say it is we have 2 completely independent programs running completely separately from each other. They have nothing in common with each other at all. So have their own separate execution flow. They have their own separate memory space, stack, heap. They are separately garbage collected at different points in time, and they are really completely 2 separate programs. And the only way they can actually work together, cooperate, is by sending themselves messages, which is also known as message passing concurrency. So again, a bunch of different ways how you can do this. In Elixir, the most foundational way would be the function called send, which you can invoke to send a message to another process. So somehow you address a process, the target, the receiver, and send it a message. And the message is an arbitrary piece of data, whichever term you can construct in Elixir. And then on the receiver side, you instruct the process to pull one message from its mailbox, which is sort of like a FIFO queue. And then you do something with this message. So if it helps, you can think of this as being similar to the idea of microservices, because there you have a similar kind of approach. two microservices are two completely independent programs, like typically two OS processes. They have nothing in common, and therefore the only way they can work together is via some form of message passing, like using HTTP requests, for example. And we have a question, or?
Yeah, how do you reference process B? How do you get a reference from process B? The previous slide, you didn't get any.
It's a complex topic in itself. You're going to see a little bit more examples later, but there is, of course, an idea of a process ID. You can somehow reference a process. Okay, so right, with microservices, you have the similar idea. You have two independent programs, and you use some message passing to communicate with them, like HTTP requests. Here you have the similar idea, except, of course, there's no networking involved. There's no HTTP protocol, no serialization, deserialization, and the mechanism is supported directly by the language, and in fact, it's supported directly by the runtime. And so let me briefly explain what happens at runtime. So let's say that you have implemented a system in Elixir somehow. You're going to have a project, where a project is basically a folder structure of a bunch of source files. And then you somehow start it. You invoke a single command to start that thing. What happens is a single operating system process is started, just one OS process, your own instance of Beam, the Erlang virtual machine. And this is where the entire system is running, in that single OS process. In there, you're going to have a bunch of these small, sequential, independent, lightweight programs, these processes, these things that you spawn on your own from within your code whenever you want to. And you're going to have a bunch of these things running. Like, think in terms of thousands, hundreds of thousands, millions, like the maximum limit imposed by Beam being around 130 million of these processes. So these things are quite cheap in terms of memory overhead and startup time. And we really run a lot of them. Now, internally, what happens, Beam employs a couple of OS threads called schedulers. By default, you're going to have one scheduler per available CPU core. And then the schedulers are responsible for executing these processes. So a naive version, how you can think of it is, imagine that there is a single queue of processes pending for execution, and then each scheduler somehow pulls one process from the queue, runs it for a little while, puts it back to the end of the queue, takes the next one, rinse and repeat. The real deal is, of course, way more sophisticated, but this simple approximation is going to work for our needs. And that's it. It's, in my opinion, not really rocket science. It's actually incredibly simple in its nature. But now it begs the question, like, what do we do with this? How do we use this thing? How do we split things into processes and to what purpose? And to demonstrate this, I have prepared a series of demos. So for that purpose, I have written a small example demo system in Elixir, which is already started on this machine as a background service, as a headless daemon, if you will, running or started pretty much in exactly the same way as I would have started it in real production. So it's a single Beam instance, it's a single OS process, and everything that you're going to see is powered by that single OS process, nothing on the side existing which supports that system. So the first thing I'm going to show you is a sort of an internal dashboard where I can generate some synthetic load. I can start up some jobs, and each job is a process, that simple sequential program. And so let me start up some jobs, which are going to simulate some usage on our system. And within a matter of a single second, we have 10,000 processes running around, 10,000 of these independent programs running around our system. And each of these programs, each of these processes runs in an infinite loop. Within that loop, it runs a short CPU-bound loop to generate some load, to simulate some synthetic load. And then it sends a message to a well-known process in the system, like a singleton, well-known, well-addressable process in the system. Basically, it indicates a success in the current iteration. Then it sleeps for a single second, rinse and repeat. And then we have that other process, in fact, a couple of other processes collecting this data and working together to propagate this to whichever user is observing this page. And so what we see on the page are some basic metrics, if you will. So most notably, the chart on the left indicates a reported rate of successes per second. As you can tell, we are roughly in the area of expected 10K successes per second. You may notice that the line is not completely perfectly aligned, perfectly flat. So there are going to be some oscillations, first and foremost because the logic is not really perfectly synchronized. And then, in addition, because there are other things running on this relatively modest machine beside the system itself, right? So most notably, this browser is rendering these charts very frequently using SVG. So expect some oscillations that are going to be maybe even a bit larger, but roughly we do expect to be in the area of 10K successes per second. Now, this system here is powered by a single scheduler thread. By default, it would actually use 4 on this machine, but I have deliberately downgraded it, hard-coded it to use 1 to make some points more obvious. And so all of the processes are running on that single scheduler thread. It's effectively a simulation of a case where we have deployed the system on a machine with a single CPU core. And as you can tell here on the right, that single scheduler is currently not super busy. So we have like a moderate load operating at around 20% of our maximum capacity. And okay, at this point we have like some synthetic users using our system at the rate of 10K operations per second. And now it's time to start using it ourselves. So I'm going to open up a user-facing page, which, as you can tell, is not really super spectacular, but it captures what I believe is a gist of any web-facing system. And that's the fact that there is some place for a user where they provide their input, and then the system chews on this input and produces some output. And in this particular case, the input is a positive integer, a natural number. And so when a user submits the input, the system computes the sum of the first 10 natural numbers, right? So 1 plus 2 plus 3 equals 6, and 1 plus 2 plus 3 plus 4 equals 10. Again, not super spectacular, but gives us a little bit of context to go on with. Now, let me first explain the process structure powering this piece of functionality. So when the user visits this page, and in fact any page that you have seen and you will see, a WebSocket connection is established between the browser and the system itself, and all the communication takes place via that WebSocket connection. So like a browser on the behalf of user submits a request, give me the sum of the first 3 natural numbers, the system processes this and then returns, or not returns, but sends the result asynchronously at some later point in time, and this is of course then rendered. In terms of process structure, each WebSocket connection is managed by its own process. So here we have a situation of exactly 3 people simultaneously connected to the system. If we have 1 million people connected to the system, we're going to have 1 million of these connection processes. And maybe in the later time, there's no one around, and then we're going to have 0 of these things. So they are quite dynamic in their nature, that they tend to come and go depending on the usage patterns. Now, the interesting thing happens within a single connection. So the calculation itself is in fact performed in a separate one-off process. Right, so like I submit a request, give me the sum of the first 3 natural numbers. The connection process spawns another process, which is the calculation process. And then the result is computed there. The calculation process sends the result back to the connection. And then the connection, of course, forwards it further to the browser and ultimately the user interface. And meanwhile, the calculation process stops, terminates normally. Right, so these things are, again, very ephemeral in their nature, very dynamic. And now it begs the question, you know, like why do we have this process structure? I definitely have not chosen it randomly. So basically the main reason why I have opted for this structure is to improve fault tolerance and ultimately high availability of the system. The ability of the system to produce service and push forward even when there are some problems in production. And as is the case with any other real production out there, this system suffers from some problems, some faults, some bugs. And we're going to explore some of these bugs. So the first one, let me just refresh this. The first one I'm going to show you is a simulation of what I personally would say is quite possibly the most frequent example of a problem that occurs in production. And this is a situation where we haven't considered some special cases, some edge cases, and then we end up with a runtime exception, unhandled exception on the server side, like square root of -1, division by 0, undefined is not a function, and so on and so forth. And here, the particular problematic input, which simulates this situation, is the lucky number 13. And so when I submit this number, I get an error, which doesn't really look super exciting at this point. But let me show you the log. Right? So here I'm tailing the log of my system. Again, the system is running as a background service, so no console running in front or something like that. So what we see in the log, we see some runtime error, and we see that something called task has terminated. And in terms that you understand, given what I said previously, this essentially means that the calculation process has crashed and burned. There was some unhandled exception in the calculation process, and it crashed. Now, an important thing about Beam is that when a process crashes, everything else progresses, right? So most of the system still works. And so like when we have a bunch of these crashes, I'm just going to generate them here, what we see on the dashboard is still a stable progress of the system at the expected rate of 10K successes per second. So most of the service is still up and running, and most of the users don't really see this problem. And this is a big important point. We are separating failures by separating things into different processes. Now, another side of the story is that a failure, while not an abrupt event, is also not a silent event. So when a process crashes, or more generally when it terminates, whether normally or abnormally, any other process in the system can get a notification about it in the shape of a message. And that's in fact what happens here. Right? So remember, we have the connection process and the calculation process. The calculation process terminates or crashes, connection process gets a message about it, stating that process foo has died because of the reason bar. It figures out the role of foo, and then it wires up this information to the user interface. And this is why we are able to report the error correctly, right? We have not lost the connection, and we were able to report the error even when we have the unhandled exception. And so, while not immediately obvious, this is what many people from the Vim community would say is the most important reason to split things into processes, to separate failures, right? To get better fault tolerance. Another very important reason, in my opinion, is to separate latencies. And to demonstrate this, I will show you another bug, another problem that exists with this system. And this is the fact that the implementation of this calculation itself is not really done in a super efficient way. It's in fact quite naive, very brute force kind of implementation that just runs a CPU-bound loop going from 1 to n and computes the sum along the way, like 1 plus 2 plus 3 plus 4, and so on and so forth. And thus, if a user submits a large enough input, then we're going to have a lot of CPU-bound processing. Right? So like I'm going to try here with the magical number of 9 nines. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And this thing is now calculating, right? It takes some time. Now what we can see on the dashboard here, that single scheduler thread that we have is maxing out at 100%. And this is going to take for like some 10 seconds or so. Let's wait for it. There it is. It's done. And here we see the result. But the very interesting thing here is that we still have a stable success rate of 10K successes per second, despite the fact that this is a single-threaded system, right? Remember, all of these processes are running on the same thread, and there is no yielding or any sort of trickery done in the implementation itself, right? So how does that even work? The thing is that Beam Scheduler performs very frequent context switching, like in less than 1 millisecond intervals, and it does it with proper preemption. So no matter what a process does, be it IO-bound or CPU-bound, it gets preempted or it gets switched out very, very quickly. And by doing this, Beam essentially favors a fair distribution of CPU time for every single activity in the system. Or in other words, it promotes the progress of the system as a whole at the expense of the maximum efficiency of any single activity in the system. And this makes perfect sense in a software system where you're running a bunch of different, mostly mutually unrelated activities. And it's a great example in my mind, in my opinion, of how Beam implementation is really geared, it's really fine-tuned towards software systems at the expense of any other type of software out there. And so, to tie it all together, right, we use processes, in my opinion, to separate failures and to separate latencies. These are the most important reasons why I split things into processes. And tying it all together as a single user, I'm going to try 4, 5, 6, 7, 8, 9. I'm going to try this CPU-intensive input, and the connection is still available, so I can provide some other input. I can generate a bunch of errors. And what happens is we still have a stable progress for the rest of the people here, and we still have a stable progress for this particular user here, and we got our long intensive computation computed. This is the system which progresses, which stays on top of the game even when there are some problems happening in production. So like despite a couple of holes that we have, our ship sails smoothly, it doesn't sink, and it provides most of the service to all of its users. And this, in my mind, is what high availability is about. It's not about chasing some mythical amount of nines of uptime. It's about having a system which is there for its users, which is ultimately its primary, if not the only, purpose. So, okay, we have a nice, highly available system, but of course, ultimately, we still need to fix these problems. Because until we do, there will be some amount of unavailability. And then in particular, there are some kind of problems which are which can be possibly threatening to the very existence of the system itself. And so here I'm going to show you yet another problem which is quite insidious. And this is the case where a user submits a negative number as an input. So I'm going to try with -1. And what happens here is we see that it hasn't really returned, right? It's calculating. So we shouldn't really have accepted this input in the first place. It's not a valid domain value, right? But once we did, we should have calculated it already. But we didn't, and in fact, what happens here, you can see on the scheduler, we're maxing out constantly. We basically have a program, an activity gone rogue, running an infinite CPU-bound loop, like an equivalent of while true semicolon, if you will. And that's obviously not quite good. Now, again, good news, owing to our judicious usage of processes and the way how Beam deals with them, we have a stable system which still progresses at the expected rate of 10K successes per second. So it works for other users, it works for this user, and this is all well and fine. But of course, ultimately, we need to fix this problem, because unless we do, the system is eventually going to grind to a halt. right? If a user retries this input a couple of more times and other users stumble into the same problem, we end up in a situation where the system is spinning a lot but really produces nothing useful in some reasonable amount of time. So it's imperative for us to quickly figure out what the problem is here and to fix it before things, completely blow up. And that's what we're going to do. I'm going to put my operator hat on. I'm going to pretend that I don't know what happened here. All I know is that I got some alert notification informing me that my CPU usage is at 100%, and I need to figure out the problem. Right, and so what I'm going to do, I'm going to SSH to the server. There I am, and I'm taking a look at the logs. What do I see in the logs? I see nothing, right? The log is completely statical. I see some previous errors. These are the number 13 problem, so that's all well and fine, but it doesn't really help me with this particular problem. And so that doesn't really look promising, but not all is lost, because Beam is a runtime which is highly debuggable, introspectable, observable, if you will. Right? So Beam allows us to hook into the running system and peek and poke inside it and get a lot of useful information. And I don't need to set some special flags, restart the system and whatnot. I can do this by default. And that's what we're going to do. I'm going to invoke the particular command to do this thing. It's remote console. And at this point, I have a so-called IEX shell session or interactive Elixir. Basically, here I can provide Elixir expressions which are running in the context of the running system, right? So like if I ask for this sum, it's calculated on that single scheduler thread. And always bear in mind, we have a single-threaded system, and we have these 10K operations per second running, and we have this single activity gone rogue, and yet everything works. And here in the shell, I'm also the user of this system, right? So owing to Beam's scheduling, I am actually able to even do this, to debug the system itself. So, okay, the question is who is burning our CPU, right? And it has to be one or more processes. And so the first thing I'm going to do is I'm going to list those processes. So process.list. And I get a list of PIDs. That's what you asked about earlier. These are the process IDs, right? So each PID is uniquely identifying a process in the system. And once I get the list of processes, then I can ask my runtime, ask the Beam about the properties of each process. So let me take the head of this process list. And I'm going to feed it to the function called process info. And I get a bunch of properties for that particular process, as reported by the Beam itself. And for our particular scenario, we're interested in a property which is called reductions, or reduction count, and this is a non-negative integer which is roughly proportional to the amount of instructions executed in that process since the dawn of time, right, since it was born. And so to figure out which are the busiest processes, I need to take reduction counts now, do the same thing in some future moment, split the difference, sort descending, and I have a top-like view. And this is like pretty mechanical to speed things up and reduce the error surface in this demo. I wrote myself a helper function for this, but even without the function, it would be like quite trivial to do this thing. And so I invoke runtime.top, and it gives me the top 10 CPU spenders in the past second. So I get a list of maps. Map is a key value structure. Under the key PID, we have the process ID. And then under the key CPU, we have the percentage of CPU usage in the past second. And as we can see, the busiest process is by far the busiest. It's the process with the PID 0, 126050. And so I'm just going to run this thing. This is our primary suspect now, and I'm going to run this thing one more time to make sure that it's the same process. And let's check it out. Sure enough, it's the same process, and so this is our culprit. Right, and within a matter of a few seconds, I was able to quickly sift through all these tens of thousands of things running around the system and find the problematic piece. And now we're going to drill into that problematic piece. So I'm going to run this runtime top one more time, take the head of it, the top busiest process, take its PID property and take it into a PID variable. And there we have it. And now I can ask my runtime something about this particular process. And always bear in mind that this is a program gone rogue. It runs an infinite CPU-bound loop, doesn't yield, doesn't talk to anyone, doesn't answer to anyone, but we can still get a lot of information if we ask the runtime, the Beam itself, directly about it. So I'll invoke a function called process.info again, and I'm going to ask for the current stack trace, which I believe is pretty self-explanatory. And so we get a stack trace of this particular process. And we're going to analyze it a little bit later. But first, I'm going to progress forward and gather a bit more data. I'm going to trace the dynamic activity in this process. We're going to take a look at which functions it's executing. So for this purpose, I also wrote a helper function called runtime.trace, which traces the function invocations in this particular process for at most 1 second or 50 function invocations, whichever takes place first. And as we can see, it's 50 function invocations. And we're going to take a look at this a bit later too. But at this point, I have gathered all the information that I need to properly analyze and understand the problem. And before I do that, I'm going to terminate this process. I'm going to ask the runtime to stop this process by sending it an exit signal. So I invoke standard library function, process.exit, the process ID, and the reason I'm using a special reason called kill, which is effectively kill -9 at the beam level, at the level of this nano pico activity. And as soon as I invoke this thing, what we can see on the dashboard is that the scheduler usage drops to expected level. And of course, nothing else was disturbed in the process, so we still have stable progress of 10K successes per second. Meanwhile, for the user, the error has been reported. Again, courtesy of how we split things into processes. The calculation process itself was brutally killed, and you cannot really try catch your way out of that one. But because we have another process which gets the information about it, this is the connection process, we are able to consistently report error information back to the user interface. So this process exit thing, it's like a seemingly simple thing, but one which is, as far as I know, exclusive to Beam in terms of guarantees. This is essentially a first-class cancellation implemented at the runtime layer, right? And so super simple to use with very strong guarantees. And here I'm invoking it from the shell, but typically we in fact invoke it from the code, whether directly or through some higher level abstractions to perform cancellation like a timeout-based cancellation or user-induced cancellation, single line of code, and does wonders. But anyway, let's go back to the data that we've collected. So the current stack trace essentially gives me a context where that particular program was in, right? And so I see the function that it was executing, and I see a module. And module is just a namespace, just a bunch of functions bundled under the same name. And then I see the file, and I see the line number, and this puts me to the proper place into the code. And then from the dynamic view, I see a bit more interesting information. So I can see that this thing here was actually constantly recursing. It was running a constant recursion, which is an FP equivalent of a constant loop. And furthermore, I see the state of each step of the loop because I see the parameters of this function, right? So I can see that the first parameter was always increased by number 1. The second parameter is always -1. And then the third parameter increased by some not immediately apparent amount. But given this data and the context, the current stack trace, which puts me to the proper place in code, I am able to figure out the problem. And the gist of the story is that, so this is the module, and this is the function right here. The gist of the story is that this code really assumes that the input is a positive integer, and it doesn't work for any other kind of input. But that's actually fine, because our business domain are positive integers, natural numbers, and this piece of code is running relatively deeply in our system. And so this is where we have the symptom. But the cause, in my view, happens at the edge of the system, right, where we're accepting user input. And we shouldn't really be allowing all these invalid inputs to propagate throughout our system. We have to discard them there. And in fact, so this is the edge of the system. This is where I'm accepting users' input. And in fact, when we take a look at the code, I'm already discarding some inputs, right? So I returned invalid input for some particular cases. But obviously, I haven't considered all the edge cases. It's a classical kind of bug. I haven't thought of all possible scenarios, and so now I have to fix this scenario, which I'm going to elegantly do by just uncommenting this line of code. Again, for demo purposes, right? All is fair in demos. And while I'm at it, I'm going to fix the remaining previous 2 problems you have seen, right? So we had a problem of problematic number 13, the edge case. There it is, I fixed it. And then we had the problem of suboptimal calculation, and to fix that one, I need to reach for a little bit of high school level math. So the sum of first n natural numbers is n times n plus 1, and then I need to divide all of this by 2. And I have actually tests which are verifying all of this, just to make sure that I didn't make any mistake. There it is, everything is passing. And so now I'm going to invoke an admittedly hacky task, which is going to deploy these changes to production. So it's going to recompile these 2 modules and bring them to production without restarting the production itself. How do we know the production has not been restarted? Because we can see here on the dashboard that we still have the stable progress of the 10K successes per second, but has it been fixed? So without refreshing the page, -1, invalid input, 0, invalid input, -1 to 3, invalid input, number 3 still works, 4 works, 13 now works, and then a bunch of 9s. I'm not even going to count them at this point because this thing is fast as a lightning bolt now. So essentially, what happened here? We had a system with problems, and it was staying on top of the game, and it allowed me to approach the system and look from inside it to figure out what the problems are, right? And I was able to quickly fix those problems and deploy them to production without disturbing anything in the system itself, right? The other activities. And this is like, as a writer of systems and ultimately one of people who is responsible for managing those systems in production, this is what I want from my tool. right? And this kind of level of utility function service, that's what I want from my tool. This is obviously what Beam gives me. I am not aware of anything else that comes even remotely close to that level of service. So anyway, the last demo I'm going to show you is related to Beam's inherent support for distributed systems, right? So it is in fact possible to start multiple Beam instances, and typically you want to start one per each separate machine, but you can start, of course, multiple on a single machine. And then with a single function invocation, you can establish a TCP connection between two instances. And at this point, you have something which is called a Beam cluster. And then these instances are called nodes. And once you have a cluster, you can programmatically do some very interesting things. So using like the main language of your choice, Erlang and Elixir, you can enumerate the nodes in the cluster. You can subscribe to join and leave events. You can spawn a process anywhere in the cluster on any node. You can send a message to any process anywhere in the cluster, and you can receive messages from other processes anywhere in the cluster. And for the most part, the code, in fact, stays exactly the same, because in fact, in Beam, concurrency and distribution are one and the same thing. And so let me show you another page. This is a dashboard where I can start up some named services. And a service here really means a process, nothing more than that. And we're going to start a process somewhere in the cluster, and we're going to give it a cluster-wide name. Now here I can see the list of nodes in the cluster, and currently we have just one node, so this is not really super exciting. And therefore I'm going to start another node. This one is going to be started in foreground. So system node 2, and immediately we see that node 2 is running, is a member of our cluster now. And so now I provide some name and submit, and then what happens is the system somehow picks a node, starts a process on that node, and gives it a cluster-wide name foo, right? And so now when I click on this thing, on the server side, the system will discover that process using the name foo, and then send it a message. And then the process is going to send that message back, and we are going to report it to on the user interface, right? So when I click, I get this entire string. Everything here is shaped within the process, which is globally known as foo, okay? And so we can see that the process, in fact, knows its own name, so it has some kind of a state, and it also, of course, can deduce the node where it's running at. And now if I start another service, let's name it bar, and it just so happened that bar has been started on another node, but you know, for us, it still works exactly the same way. So I have like kind of a load spread, you know, I'm spreading these services across my cluster. And what happens if the node dies, right? So I'm going to stop this node 2. And what we see here is that a bar has been resurrected on node 1. So this is like fault tolerance I'm dealing with, even with crashes of individual machines. And when I click on bar, now of course bar responds from node 1. Okay, so full disclosure, complete honesty, this all looks well and fine, but I would say that Beam distribution is sort of plagued with a bunch of issues, serious issues, you know. So like, while many people do use Beam distribution, distributed Beam in production, there are also many people who would tell you, like, maybe not use that thing. I'm not going to go into those issues, you can ask me about it later, but in my view, they are serious and they exist on all levels, starting from the runtime level all the way to the high-level libraries that we use. That said, I would also say that these issues are purely mechanical, which means that they can be fixed in the implementation without significantly changing or without changing at all the interface, the contract, the way we use this thing. And this is where I see a lot of potential, and that's exactly, or that's actually what I want to explain. So I will briefly give you a very quick code walkthrough. So here we have the module which is powering this distributed named service, right? And within that module, again, the module is just a bunch of functions. We have another submodule called local. Now this piece of code here is completely agnostic of the fact that distributed Beam is used. Doesn't care, you know, you can use it, you don't have to use it, works exactly the same. This is just basic concurrent Elixir, and if you want to do some concurrent Elixir, sooner or later you will have to learn a little bit of this, which is not really rocket science. And now the question is, how do we turn this thing to be distributed? And there are exactly 3 things I've done. Thing number 1, in another file, which is called mix.cx, which is the part of the same project. This is where I'm configuring the project itself. And within that file, I have a section where I'm defining dependencies of the project, like the libraries on the framework which I'm using. And one of my dependencies is called Swarm. And Swarm is basically like a higher level distributed service orchestrator. It gives me a high level interface which allows me to start a process somewhere in the cluster and give it a cluster-wide name quite easily, right? And Swarm is a dependency, and in Elixir, like in any other language, Beam or not Beam, a dependency means bringing in some code, right? Some functions which I can invoke. However, in Beam languages, a dependency may also bring activities processes, right? And so courtesy of this single line of code, when I start my system, Swarm is going to start some of its own processes which are related to the Swarm functionality. So these processes are going to watch for nodes joining and leaving, and they are going to manage the cluster-wide state, the association of names to processes. And all this happens courtesy of this single line of code. Essentially, I am running this distributed service orchestrator directly in my system. And because in my mind, this thing is a part of my system, it's the best place to run it. Like, what's the better place to run a part of the system, if not the same place where the rest of the system is running itself? And anyway, once I have Swarm running, then starting a named service somewhere in the cluster boils down to invoking a particular Swarm function which does exactly that. So it's going to somehow pick a node and start a process there, and it's going to manage the association between the given name and the process. And then once I want to discover and invoke this service, given its name, I invoke another Swarm function, I give it a name. It gives back a PID, which is again a unique piece of information identifying the process in the system. And in this case, the system is a cluster, not just a single node. And so PID is locationally transparent type, right? It can work for local processes and it can work for remote processes. We don't care. The vast majority of the functions which are working with PID data type don't care too. And so I get a PID and I just pass it to the distributed beam agnostic function and the thing just works, right? 3 lines of code to make this thing distributed, nothing else running on the side. No extra OS process, no container, no virtual machine, nothing as a service is employed here. In fact, I'm even completely disconnected from the network. And so this thing is super integrated. Right, everything is in fact implemented in Elixir, so there is, like, even the user interface itself is driven by the Elixir code. There is no JavaScript here. This is all very technically uniform, and this technical uniformity is the last thing that I want to discuss in my current talk. So this table here, originally published in my book Elixir in Action, tells a true story about 2 systems I was working on side by side around the beginning of this decade. And what happened in System A was that our first chosen technology, our cornerstone, our foundation, was a technology that didn't really have proper support, if any, for the challenges inherent to software systems. And we were building a software system. We had those challenges, and in order to solve them, we had to fall back to the level of the operating system, right? And so we had to run a bunch of OS processes and reach for other languages where we needed a better concurrency story. And we also, of course, had to reach for third-party products, and we fulfilled our needs. However, the technical complexity, footprint, the barrier, if you will, of this solution is really, really high. Like, imagine a junior landing to this thing. How much of the things do the technical concept, technical things do they need to learn before they can confidently work on any part of the system? System B, implemented in Erlang, running on top of Beam, the runtime which, as you have seen, has a rich support for software systems. It is in fact sometimes said that Beam is an operating system for our code. And if I have the operating system directly in my runtime and I have the language as the main interface, then I don't need to fall back to the OS level, and indeed we didn't, right? So we were able to fulfill all our needs in Erlang in the same language, in the same project, have it run as a single OS process at runtime. Now, it goes without saying that these solutions cannot fully compete with full-blown third-party products. So they don't have all the bells and whistles and fancy performance, but they worked for our needs just fine. And what we got in return is this total technical uniformity, which of course is not a goal in itself, right? We should not strive for uniformity for the sake of uniformity, but I do believe that it can bring a lot of important benefits that take place in all the phases of a software development cycle. So like, if my whole system is implemented in a single piece of technology, let's say Elixir, right? So one language, one project, one OS process per each machine in the cluster, then it's clearly easier to work with it on a daily basis, right? So like, starting from setting up a development machine, and then, writing some code, writing tests, setting up CI, deploying a single thing has to be way easier than orchestrating a deployment of 5 to 10 different moving pieces, and then managing the system in production. There is like one thing we hook into. There is one thing where we collect metrics and logs. There is one thing we debug, which, as you have seen, of course, is where Beam particularly shines. And then on top of it all, and I would say by far the most important benefit, is the fact that the teamwork in general is improved, because the technical bar is significantly lower. There are less technical things to learn, and that's a good thing. Right? A new developer comes on board, they learn themselves a bit of Elixir, and they can immediately contribute to any part of the system. And so we don't need to have all these narrow specialists. We don't need to have like a Redis specialist, Nginx specialist, etcd specialist, Zookeeper specialist, Kafka specialist, Kubernetes specialist, and so on and so forth. And we don't need to wrestle with all these YAMLs and inis and JSONs and TOMLs and XMLs and other kind of ad hoc DSLs and their quite substandard tooling. It is in fact possible, it is perfectly viable to describe the entire system using a single language, which is Turing complete, gives us full integration to the underlying operating system, and it gives us full flexibility, compile time and runtime to make whichever variations we want on a case-by-case basis. And these are, in my opinion, some terrific benefits to be reaped. And the reason why they can be reaped is because we have something like Beam as our foundation, right? And so this is where I see the biggest potential of Beam languages, which is admittedly not still fully realized. We're maybe like halfway there, but I do hope we'll get there. And like imagine the following story. You want to build a small to medium web-facing CRUD. And what you do is create a new Elixir project, bring in a couple of dependencies, and 5 minutes later, you have everything. You have like proper support for distribution. You have SQL-based persistence with replication, everything running directly in that same project in the single system. Now, this is what I call a simple start, right? Because it moves a lot of technicalities out of the way, and it allows me to focus on the core challenges that I'm supposed to solve. Yet at the same time, the solution is implemented in a full-blown Turing-complete language, and it's running on top of Beam, this wonderful runtime that has been around for like, what, 3 decades, has been extensively battle tested in different projects of different shapes and sizes. And so I can really be confident that down the line, if I need to, I can deal with highly complex challenges at a very large scale without having to rewrite everything from scratch. And in my view, this is a win-win combination, right? So the artificial trade-off of having to choose between a quick start technology and the long-run one disappears, flies out the window, and I get both in the same piece of technology. And this is all, in my opinion, possible, not realized yet, but possible, owing to Beam, this wonderful runtime, which is, in my view, indeed the soul of Erlang and Elixir. So before I part, a couple of parting gifts. I'm the author of the book Elixir in Action. Only today, it's 50% off with the following code up there. And then for the rest of the days, you also have the 40% off code. I'm also giving away a couple of copies for free. So I have 2 hardbook versions and a couple of more of ebook versions. And if you want to grab that, just approach me after the talk and ask for it. You don't have to pretend that you're interested in anything else. Please rate this session. Let me know what worked, what didn't. I'm going to return back to this slide in case you want to grab those codes. And thank you.